Hello, my name is Raymond. Today, I would like to talk to you about image denoising. Let's begin with some background information about it. From these two images, we can see the annoying noise reducing the quality of the images. Image noise is mainly caused by these four reasons. The first reason is the exposure time may be too long. When shooting night scenes, it is easy to produce noise when the shutter time is more than 1 second. The second one is about compression, like JPEG. This noise due to JPEG compression is called block noise. Image noise can also caused by unsharp mask. This noise is produced by sharpening the edges of a small image. The last one is the area of the sensor may be too small. As image denoising is an indispensable step in many practical applications, kinds of image denoising models is proposed. There are two main categories: image prior-based methods and discriminative learning methods. The former one includes these four models such as NSS, MRF. The latter one is developed recently, including CSF and TNRD. Despite the high denoising quality, most of the image prior-based methods typically suffer from two major drawbacks. First, these methods involve a complex optimization problem in the testing stage, making the denoising process time-consuming. Hence, most of the prior-based methods can hardly achieve high performance without sacrificing computational efficiency. Second, they involve several parameters that must be chosen manually. As discriminative learning methods, those CSF and TNRD have shown promising results toward bridging the gap between computational efficiency and denoising quality. Their performance are inherently restricted to the specified forms of prior. Therefore, instead of learning a discriminative model with an explicit image prior, we propose a more effective Gaussian denoiser, which we call DN-CNN. This model has the following characteristics. We treat image denoising as a plain discriminative learning problem to be specific, separating the noise from the noisy image by feed-forward convolutional neural network. Rather than directly outputting the denoised image, the proposed model is designed to predict the residual image. In other words, DNCNN implicitly removes the latent clean image with the operations in the hidden layer. Here are advantages of using CNN. Number 1. CNN with super deep architecture is effective in increasing the capacity and flexibility for exploiting image characteristics. Number 2. Considerable advances have been achieved on regularization and learning methods for training CNN. These methods can be adopted in CNN to speed up the training process and improve the denoising performance. Number 3. CNN is well suited for parallel computation on modern powerful GPU, which can be exploited to improve the runtime performance. The first step of training a deep CNN model for the specific task is network architecture design, including network depth and network architecture. For better trade-off between performance and efficiency, one important issue in architecture design is to set the proper depth for DMCNN. We set the size of convolutional filters to be 3 times 3, so the receptive field of DMCNN with depth of D should be 2D plus 1 times 2D plus 1. By fixing the noise level sigma equals to 25, we analyze the effective patch size of several leading denoising methods to guide the depth design of our model. The table below summarizes the effective patch size adopted in different methods with sigma equals to 25. It can be seen that the effective patch size used in EPLL is the smallest. The next part of network architecture design is network architecture. There are 3 types of layers shown in the figure with different colors. For the yellow layer, filters are used to generate feature maps and ReLU. For the blue layers, filters are used to batch normalization and then added between convolution and ReLU. For the last layer, the number of filters is equals to image channels, and they are used to reconstruct an output. Reducing boundary artifacts is also an essential part of network architecture. In this model, we directly pad zeros before convolution to make sure that each feature map of the middle layers has the same size as the input image. Then, we find that the simple zero padding strategy doesn't result in any boundary artifacts. This good property is probably attributed to the powerful ability of the DMCNN. Then, we set an experiment to test our model. We crop plenty of patches to train 2 different models based on DMCNN, and then test them using 68 images from BSD68 and 12 images that show below, which are widely used. Here is a sample of the result. We compare models with data from 2 aspects, denoising quality and runtime. It can be seen that BM3D, WNNM, EPLL tend to produce over smooth edges and textures. NLP also produce textures. As we can see, TNRD is likely to generate artifacts in a smooth region while preserving sharp edges and fine details. In contrast, DMCNNS and DMCNNB can not only recover sharp edges and fine details, but also yield visually pleasant results in the smooth region. In addition to denoising quality, another important aspect we concern is the runtime. It can be seen that the proposed DMCNN can have a relatively high speed on CPU, and it is faster than 2 discriminate models, NLP and CSF. Though it is slower than BM3D and TNRD, by taking the image quality improvement into consideration, DMCNN is still competitive. Since CSF, TMRD, and our DMCNN methods are well suited for parallel computation on GPU, we also measure the runtimes on GPU. For the GPU time, the proposed DMCNN achieves very appealing computational efficiency. In conclusion, in this paper, a deep convolutional neural network was proposed for image denoising, where residual learning is adopted to separating noise from noisy observation. The batch normalization and residual learning are integrated to speed up the training process, as well as boost the denoising performance. Unlike traditional discriminative models that train specific models for certain noise levels, our single DMCNN model has the capacity to handle the blind Gaussian denoising with unknown noise level. Extensive experimental results demonstrated that the proposed method not only produces favorable image denoising performance, but also has promising runtime and GPU implementation. Here are the references of my presentation. And that's it from me. Wish you all the best, and thank you for your attention and teaching me for 2 semesters.